I'm Matteo. I'm a second-year PhD student in Amanda's group. And today I'm going to talk about heterogeneous multi-robot reinforcement learning. This is a paper we will be presenting at AMAS 23. So first of all, the idea is that the goal of our lab is to achieve collective intelligence in multi-robot systems. And these are problems where it's not enough to have more robots to enhance performance, and more robots are really needed to solve the task in the first place. And some examples from nature and from robotics are shown here. These problems are hard, and thus solving them with first principle is usually unfeasible in a number of robots. So that's why we usually look into learning solutions. But turns out that still looking at nature, there is a lot of diversity in nature, and this comes at a behavioral or at a physical level, or also at a functional level. And nature really achieves greater performance and collective intelligence by leveraging this heterogeneity that it has. So when it comes to achieving collective intelligence, we think heterogeneity is key. And since we are tackling the task of collective intelligence through learning, it's a natural step for us to look into methods to leverage heterogeneity while learning multi-robot policies. So first of all, one of the first contributions of the paper is to try to answer the question, so how can a system be heterogeneous? And so what do we mean when we say that we have an heterogeneous multi-robot systems? And we try to do this by introducing this taxonomy. And at a high level, we have these two different domains. So there is a physical heterogeneity where the robots or the agents are different in their hardware. This is sensors, actuators, and so on. And then there is the behavioral side where the robots are different in their software, in their controllers. And the behavioral heterogeneity further divides in when the robots are behaving different to tackle the same objective, or when the robots are behaving differently to tackle a different objective. And these are the objective functions. And note that same objective or different objective do not directly correlate with cooperative or non-cooperative, because you can have same objective which is cooperative or non-cooperative, and the same goes for different objectives. So there is not a one-to-one mapping there. So you can see that when we go and look at how these two types of heterogeneity intersect, we see that there are these 5 subclasses created by the Venn diagram. And let's see what each of these means in detail. So first, if we look at this orange area, this is systems where robots are physically heterogeneous, but they're not behaviorally heterogeneous. This means that there are physical difference, but we're trying to using a homogeneous solution at the software level. We're trying to use it to reconcile these physical differences in the software side. And you can think of multi-robot SLAM, where we have robots with different sensors, but at the end of the day, we're trying to build a homogeneous map and reconcile their differences in this map. And in the learning side, oftentimes we have robots with different input spaces, one bigger than the other, because maybe one is a LiDAR, one is a camera. And what we do there maybe is padding them so that we have the same input size and we can use the same homogeneous model on all of them. So this is not really the class that leverages the best out of heterogeneity because it doesn't leverage the physical differences at the behavioral side. If you look at the red area, it's a more interesting category because here we have robots with physical differences and behavioral differences which are tackling different objectives. So you can think of in a disaster scenario when you have maybe one robot that is tasked, that has a grease grabber and is tasked with removing debris, while another robot is tasked with searching for victims with a camera. And they have different objectives, they have different hardware, and they have also different behavior. If you look at the green side, this is where the majority of the heterogeneity in robotics literature is focused on. This is where we have physical different robots, which are different behaviors and which are optimizing for the same objective. And these are tasks like heterogeneous coverage or heterogeneous task assignment, where we're trying to make the best of the physical differences of the robots by developing independent policies for each to solve a global objective, which is usually cooperative. On the last two sides, the cyan one is particularly interesting for me because this is where my PhD is focused. This is where you have identical robots which are optimizing for the same objective, but they do so with the different behaviors. And you can think of this as maybe football is an example where basically you have robots which are the same and they have the same goal, which is to score a goal, but they can develop complementary skills to do it. So some of them will be attackers and some of them will be defenders. And lastly, we have the pink area where we have identical robots which are using different behaviors to optimize for different objectives. And you can think of here is that a scenario where we have two drones that are tasked to surveil an area, and one is basically surveilling from a higher level and telling the other drone which areas to surveil more in detail. And so they're optimizing for different objectives with different behaviors, but they're identical. So this is just an overview of what an example from each category is. If you see in the paper, we have categorized existing work in robotics and in learning of multi-robot policies and fit each work in one of these 5 categories. Of course, there could be a more fine-grained taxonomy, but this as a high level serves our purpose. So after having developed such a taxonomy, what we want to do is to have a tool that enables us to learn heterogeneous policies for each of the classes that we just highlighted. And what we introduced is called HETGPPO. And basically, this is a model for learning the policies, which has a homogeneous version, which is GPPO, and a heterogeneous version, which is HETGPPO. And basically, this is simple in the sense that each agent is equipped with a policy, which maps observation to action, and a value function, which basically determines the goodness of a state. And these policies are independent, local, and distributed in the sense that each policy only has access to the neighbor communication with the neighborhoods and not with the whole state. So this can be trained decentralized, and also communicating helps overcoming partial observability of a single robot. And the difference between the homogeneous and the heterogeneous model is that in the homogeneous model, the same model is replicated n times for the agents. While for the heterogeneous model, there are really n different models where the parameters are different for the GNN, for the encoders, and so on, and they're different for each robot. And in reinforcement learning, traditionally, the homogeneous solution is used because this is more sample efficient. Basically, all the robots will benefit from the same updates. But this is not really what we want, because this would cause homogeneity in the team. So to think about it, what it means to be a heterogeneous, you can think that given an observation O, for all robots in the system, if given this observation, they all have the same output, that the system is homogeneous, while if they can have different outputs, it's heterogeneous. So what we want to do with this now is to apply these models, homogeneous and heterogeneous counterparts, to multi-robot collective intelligent tasks and analyze what's the difference between homogeneity and heterogeneity in learning. So now I'm going to ask you something. I'm going to explain this task, and then we're going to see one model solve it. And I want you to guess if this model was trained using an heterogeneous or an homogeneous policies for the agents. Basically, the task is simple. There are two agents, which are the bigger circles, blue and green, and they're tasked with going to the respective goals, which are the smaller circles. And their action is the line that you're seeing, which represents a force in 2 dimensions. And they're constrained in this narrow corridor. And what we're seeing is a top-down view of the environment. So now I'm going to play it. And we can see that in order to reach their goal, one of the agents has to give way to the other agent. So the blue agent just gave way to the green one. So does anyone have any guess if this is a homogeneous or heterogeneous training policy?
It looks homogeneous.
It's homogeneous, yeah.
Yeah, so it is homogeneous. But at first, this could be counterintuitive, because what they're actually doing is that one of the two agents has to decide to be the first to give way to the other. And if they're given the same observation, we would think that the homogeneous model would not be able to do this. So this way that homogeneous policies are able to emulate heterogeneous behavior is what we call behavioral typing. And basically what happens is that homogeneous models are able to identify which agent needs to have which role from the observations, and then it's able to assign this role in a homogeneous policy. And this behavioral typing, we try to classify a few flavors of it. First, there is the explicit flavor, where basically an explicit index is given to the agents. So I'm telling, alongside the normal observation, I'm giving to agent 1 also index 1, and to agent 2 index 2, so that the homogeneous model is able to condition on this index and output a role which is different for 1 and for 2. This is a problem, though, because basically we still have to share one monolithic homogeneous policies, which is just multimodal, and these different modes are conditioned on these explicit inputs. Another way that homogeneous model can emulate heterogeneous behavior is through inferring it. And basically, they can infer it from the observation, and they can do so in different ways, which is for agents that are physically identical and for agents that are physically different. And for agents that are physically identical is what we just saw in the video. So basically, what happens is that the homogeneous model, at each time step, each agent is seeing observations which are the relative position to the other agent, the relative velocity to the other agent, its absolute position, and its absolute velocity. So without knowing the relative position to its goal, this agent is not able to identify which one is it. But the homogeneous model is able to use this observation to say, okay, given this relative position, relative velocity, I am the one that should be giving way now, or I'm the one that should be receiving way now. And that's how it was trying to emulating the heterogeneous behavior we were seeing before. And if you can see in this graph, this is training this behavior for heterogeneous policies and for homogeneous policies. And heterogeneous policies are able to learn it immediately because one agent just learns to be the agent that always gives the way, and the other agent is always the agent that goes straight. While for homogeneous policies, it's much more painful to learn because they have to learn to infer it from the observation. They have to learn how to map observation to a role and then assign it to the agent. And so this process of behavioral typing and assigning the roles turns out that it's very brittle with respect to noise. This is because the homogeneous models are trying to infer the roles of the agents from the observation. So when the observations are noisy, basically this process will break down. And we show this for physically heterogeneous and for physically identical agent by injecting uniform observation noise at execution time. And we can see the degradation difference in the two models. And this is, again, because homogeneous models are emulating heterogeneous behavior using typing, which is using the observation, which again are noisy. And so this is how this happens. But what is more interesting is that, well, the real world is noisy, right? So instead of injecting artificial noise at execution time, what about just deploying the learned policies to the real world and see how it reacts to the real world noise? And if you look at the heterogeneous policy, basically, this is straightforward. It's learned in simulation and it's deployed in the real world, and it's in the same way that it was behaving in simulation. We can see that one of the agents gives way to the other, and the other agent just goes straight. And this is the optimal solution to the task. In the homogeneous case, it's what I just showed you in the video. Basically, in simulation, everything works fine because of the behavioral typing. But when we actually deploy to the real world, we can see that the agents start by performing the switch. They perform the switch successfully. And then at about this point, they get confused and they perform the switch again in reverse. And this is because given the observation noise, they're actually getting tricked into thinking that they are each other. And the behavioral typing that they're using to identify which agent should give way switches the roles of the two agents. So they will keep now switching until finally they will solve the task. But basically, they will oscillate between the two roles because the observations are noisy, and in simulation they weren't, and so the homogeneous models were able to use those to identify the roles. And this is the plot to translate what I just said in simulation, and we can see that the task completion over time in simulation goes well for both homogeneous and heterogeneous, while in the real world, for heterogeneous models, we can see this oscillation where this is the passage point, and we can see the robots oscillating between its behavior here, and this behavioral oscillation is caused by this deployment. And lastly, as my last slide, apart from looking into ways in which homogeneous model emulate heterogeneous behaviors and how these fail, we look at scenarios where heterogeneity is actually needed to achieve collective intelligence. And especially with two interests on performance and resilience. And what we're interested in the first task is basically, this is a passage scenario where there are two agents, which are the blue circles, which are physically different. One is bigger and one is smaller, and they need to fit through a gap, which is also asymmetrical because there is a wider gap and a smaller gap. And in order to solve the task, basically the agents have to each tackle the properly sized gap and collaborate since they are connected by a linkage. And so basically they're able to do so only if they are heterogeneous, because they have no way of observing which agent is the bigger one. And without no way of observing that, they have to develop a custom policies for each. And you can see here confirmed by the reward that only heterogeneous agents are able to do this. And another thing that we're looking at is resilience, which we already talked about a little bit. But in this case, we have identical agents. They just have they're carrying a mass on the linkage, and this is a transportation scenario, and they have to transport this mass through the gap. And we can see that with this is during training with zero noise, basically homogeneous and heterogeneous are both able to achieve 100%. But when we inject noise during training, the degradation of homogeneous is much less graceful than that of heterogeneous models. And this is again because homogeneous is using some indexing tricks to emulate heterogeneous behavior, which are brittle with respect to noise. Yeah, and this was all from my side. These are some QR code for the simulator and the paper, and I'm glad to take any question.